So we're moving on to chapter 3 now, which is the justification for quantum mechanics. Now remember, at the beginning of the semester we talked about what this class was about, and the class was about the fact that at the turn of the century, 1900, physicists thought they knew everything. So, except there were a couple of unanswered questions. And it was really the late 1800s, 1880s, to, when Einstein published his miracle papers, to the early 1920s, when these experiments were started to be better done and better understood, and some new discoveries came along that totally turned physics on its head. So that's what we're going to do in chapter 3, is we're going to talk about the new discoveries and the answers to the unanswered questions, such as how to explain blackbody radiation, how to explain line spectra, and the photoelectric effect. Those are the primary ones, and there's a couple of others. So we start in 1897, where we're still at the point in the late 1900s when we don't really know what the smallest piece of matter is. We're at the point in the late 1900s when we still don't know what the smallest piece of matter is. We're at the point today when we still don't know what the smallest piece of matter is, but we have some ideas. In 1897, J.J. Thompson discovered the electron. J.J. Thompson, like many scientists at the time, was doing experiments with cathode ray tubes. Cathode ray tubes were a relatively new thing in the late 1800s. And we'll talk about why in a second. And in these cathode ray tubes, people are able to create what are called cathode rays. And J.J. Thompson realized that these cathode rays were actually just streams of particles, streams of extremely small particles, which eventually came to be called the electron. Now, you've probably heard of CRTs. Maybe you haven't. But the CRT is what televisions used to be made out of until we got flat screen TVs on the order of what? I don't know. Early 2000s when flat screen TVs became big. But before that, they were CRTs, cathode ray tubes. What is a cathode ray tube? So the cathode ray tube is an evacuated tube, and the what's shown here is really something that looks more like a TV screen. But the earlier cathode ray tubes were just round bulbs. They look like light bulbs, really. And there's a filament in them, a filament here, a hot filament. And that's what creates the electrons. We'll talk about that in a second. Those electrons are accelerated between a voltage so that the electrons are given some speed, and then those electrons are aimed with these two sets of plates. They're aimed at different spots on the screen, so we can hit anywhere on the screen. And what a cathode ray tube really is, it's again an electron gun where we can then aim the electrons to hit anywhere on a screen, and the screen will glow where the electrons hit. That's what a cathode ray tube is. And what you can do is you can do this so fast that even though you're doing one electron at a time, or one little bit stream of electrons at a time, you can fill up that entire screen with a picture, because you can hit that screen with so many electrons so quickly that you can create an image on that screen by having the electrons hit or not hit in certain places, and make the screen glow in certain places to create an image. The glow only lasts for an instant, a short moment, less than a second kind of moment. But what you probably know about cathode ray tubes, or what you might know, is that they continually scan along these lines, and the electrons are continuing to hit. We could just do one at a time, one line at a time, but we just do it so quickly and we keep on doing it. We keep on going over and over and over again, and then as the picture changes, we hit in different places. And we just do it so quickly that your mind, your eyes, and your brain actually integrate that image and just add up all the bright spots to make it a picture, right? So we might actually have a picture here. But if you took if you took a photograph of a CRT screen in a very short exposure photograph, you would see that only part of the screen is lit up at any one time. So now let me step back and remind you that this is what J.J. Thompson used to discover the electron. So he didn't know, scientists at the time didn't know what was creating these cathode rays, this thing which we now call an electron gun, this part of the tube that we call the electron gun. Scientists didn't know what was creating the rays, but they knew that they were able to create these things by heating a filament. It's simply a hot filament. It's really just a light bulb filament. You take a light bulb filament and you put a large amount of current through there, and right, what happens? It gets light. It's bright. But what it happens is that it gets so hot that it starts to shed material, and the material that it's shedding is, in part, electrons. Because those electrons are charged, they can then be accelerated between voltage plates. So you got some voltage plates in here, and they can be accelerated, and that's your electron gun. And what J.J. Thompson discovered is that these cathode rays that they were creating by heating a filament and then accelerating them between two plates, right, a voltage between the two plates. So these electrons, oh, and by the way, you just put a hole in the plate so that the electron can keep going. That's how you shoot them. That's why it's an electron gun. You're shooting them out of this thing. You just put a hole in the plate. And what J.J. Thompson discovered is what these beams were that they were creating. They were creating these beams called cathode rays, and he realized that they were actually particles called electrons. So just to reiterate, the electron gun is just a filament and a voltage difference to accelerate those electrons, a hole in one of the plates so that they can keep going, and so you can shoot them like a gun. Boom, electrons. Okay. One of the interesting questions of the time is why there were so many of these kinds of discoveries of X-rays and electrons and things like that in the late 1800s, early 1900s. And the answer is interesting, that it has to do with the fact that it was only in the mid to late 1800s that scientists figured out how to pull a vacuum in a glass bulb. And that just opened up a huge amount of things that scientists could do if they could get a vacuum. And so in order to do these experiments, you had to have these glass bulbs, like light bulbs, right? That in order to send a current through a filament and have it light up without burning up, you had to take the oxygen out. You had to take the atmosphere out, or some of the atmosphere out, the oxygen certainly. And once scientists figured out how to evacuate a glass bulb, they were then able to do all kinds of experiments they couldn't do before. Hence, there's all kinds of discoveries in the late 1800s that simply come from the fact that they could now evacuate a glass bulb and then put in there what they want to put in there and eliminate the atmosphere, which was messing with everything. Okay, so that's the cathode ray tube. The cathode ray tube, again, is an electron gun plus some voltage plates that allow you to aim these electrons, to change the path of the electrons. And that's what we're going to talk about next, is how that works. But in addition, what scientists often did is they put magnetic fields on these as well. So they wanted to see how both magnetic and electric fields affected the charges. So they would put magnetic coils outside of the electron gun, right? So these are just coils of wire, which give you an electromagnet, in order to see what the magnetic field effect is on these charged particles, as well as the electric field effect, which is given by these charged plates inside the CRT, inside the cathode ray tube. So that's a CRT, electron gun, voltage plates to accelerate the electrons, voltage plates to aim the electrons, and then magnetic coils in order to aim the electrons as well. Now let's look at those actual effects of how you aim the electrons and how J.J. Thompson discovered them.